got to crank. So go ahead and get your book open to your first page here. We're going over chapter 4. There are 8 sections in chapter 4. We're going to be talking about the laws of exponents and scientific notation today. And then we're going to be talking about polynomials all next week. Have you taken the test? Raise your hand if you've taken the chapter 3 test. Okay, when is the last time to take it? Tonight at 11:59 p.m. It must be turned in and completed. Make sure to get that done. And then there's some days to retake it next week. You can look up the email. I think it's Wednesday of next week or something like that. But you guys can look it up. Okay, this first page is just a quick review of exponents from our R chapter knowledge about it. So let's rip through this really fast. What are some other names for exponent? Power. Going right. Power is one of those lines. Power is correct. What's another name?
Degree.
Degree, yeah, it was a brand of deodorant. We talked about that. Degree is another name. Okay, what's that? It says big number, and there's something. What's next to the big number? Little number. Nice, little number next to the big number. Very good. Okay, we learned all this. Everything we're doing right here is a review of stuff we got back in the R chapter. The 3 E's of exponents: exponential notation, expanded notation, and evaluated notation. 2 to the first, when we expand it, is just 2, right? Evaluate it, it's 2. 2 to the second is 2 times 2, which is what? 4, right? So right here on this third line, I have 2 times 2 times 2. What would I write in exponential form? Everybody.
2 to the third.
2 to the third, right? And evaluated form, what would I write? 2 times 2 times 2 equals what? 8. Okay, so finish this chart. Give you a second to do this. Okay. What's my next line? What's my exponent going to be? 2 to the what? 4th. Expanded. 2 times 2 times 2 times 2. What is that? 16, right? And then we have 2 to the 5th, right? And that is going to be 2 times 2 times 2 times 2. What does that equal? 32. All right? The anatomy of an exponent, right? What's the little number called right here? What's that called?
Little number.
Little number, or let's just call it the exponent, right? So write exponent right there, okay? All of this, 12x, down on the bottom here is called the base. So write base right there. In the base, you have a big number. The big number, I'm going to write it down. Do you know what it's called? It's called the coefficient. You were thinking about the C word there, right? Coefficient. And then obviously, the letters are called the what? Variables. And that's all part of the base, okay? So that's just a quick review of concepts we have already covered, right, a long time ago. Just kind of, it's like when we go work out, right? This is just our warm-up, okay? We're going to be teaching you about the laws of exponents. Laws of exponents are fun. They're kind of cool. So there are 5 things that I want to tell you about when it comes to the laws of exponents. And I'm going to kind of draw a little example of each of these 5. Let's go ahead and just focus on this page 365, these 5 things. So the first thing I want you to understand about the laws of exponents is they are shortcuts. Okay? When I was a little boy and I walked to school, it was about a 2-mile journey to go to school. So that's pretty good distance for little kids, little short legs. And but you could cut literally a half a mile off the journey to school by cutting through Mr. LaCroix's backyard. And Mr. LaCroix did not like trespassing. Okay? And so all the boys in the neighborhood, we get together in the morning, we go to school, we have our backpacks on, we're walking around with our little backpacks. And Jeff was my best buddy, and Brian was his little brother. And Brian was, kind of a little timid kid, and we'd get to the edge of Mr. LaCroix's property, and Brian would always say, we can't trespass. I'm like, you walked a long way to school, Brian. And so as soon as you hear Mr. Brother, he wasn't a brother. Okay? There aren't too many brothers and sisters up there. Anyways, in terms of Mormons. And so Mr. LaCroix, you'd hear his front door open, and he let his dog out. His dog come chase you. As soon as you heard that door open, man, you ran. And it was like forested and stinging nettle and all that kind of stuff. But I'll tell you what, man, if you did not go through his backyard, okay, you'd be late to school, or you had to get up a half hour earlier because it shaved off that much time. So I like shortcuts. Okay, let's talk about what does it mean to be a shortcut. Well, first of all, wouldn't you agree that, x times x times x times x times x, you want to say that or write that? Or do you want to call it x to the fifth? That's a shortcut, right? Okay, look up here, please. We're going to learn today that x to the second times x to the third equals x to the fifth. But people say, but, Brother Rich, why isn't it equal to x to the, what? Sixth, right? No FUMAR, don't smoke that dope, okay? Look at this, shortcut. Do we want to write that that's x times x? Do we want to write that that's x times x times x? Do we want to drop that down so we see it's x times x times x times x times x? How many x's? Yeah, that's x to the fifth. Okay, so the shortcut takes us there. We're going to learn about this. This is one of our laws. We're going to talk about it in depth and explain it. Right now, you want to write underneath that space there. These are two examples of how these are shortcuts. Okay? They just make things go faster. We don't have to take the long way. We don't have to write all these x's out. Okay? Little numbers behave differently than big numbers. After that, I want you to write as they should. As they should. They're different. Why wouldn't they behave differently? Look up here, please. 5 to the second does not equal 5 times 2. Okay? No. Don't smoke that dope. Okay? 5 to the second is 5 times 5, which makes 25. 5 times 2 makes 10. Those don't equal each other. Big numbers and little numbers behave differently. As they should. They are different. Okay? And we're going to see that throughout these laws of exponents. Product and quotient rules. It says they apply only to things with the same base. Okay? Look up here, please. So I told you we're going to have x to the second, and we're going to have maybe x to the fifth, and they're going to be being multiplied. We're going to say, well, that equals x to the seventh. Okay? Well, then we're going to see x to the second times y to the fifth, and that's going to equal x to the second y to the fifth. It's not going to change because they have different bases. These have the same base. Okay, so that's an example you should put with that one right there. Okay? And again, we're going to get into the laws and explain how they work so you understand more about why this is the way it is. But for now, we're just writing these examples. Okay? These next two, there's no special thing I want you to write after it. There's no order of operations when it comes to the laws of exponents. Okay? We don't first do the product rule and second do the quotient rule. You can apply them any way you want. It's like cleaning your bedroom. You don't have to, pick up your dirty clothes and put them in the laundry basket first. You could pick up the garbage and put it in the waste bin first. You could pick up your books and put them on the bookshelf first. There's no order. You can just clean, and there's no rules with this. Same thing with the laws of exponent problem. You can apply them, in any random order until it's all cleaned up. Okay? But you must memorize them. So we're going to make a chart. So let's turn to our next page. Okay? We have a chart here. You need to turn your book sideways today. So fun. So fun. Yee-hoo. Okay? Nice. Nice and big and beautiful for you here. Okay? The beauty of this chart being all kind of formatted for you. You don't have to draw this. It's all drawn for you. We're going to fill this in, though. You guys cool if I erase this? Okay? So look at the chart right now while I'm erasing. There are 4 columns. The first is the actual law. There are 5 laws of exponents. The 0 and 1 rule, the product rule, the quotient rule, the negative exponent rule, and the power rule. The next column is called hypothetical. Let's define hypothetical. What does hypothetical mean? Well, if you walk into my office and you say, Brother Rich, I have a friend that has a problem. Okay? We all know it's you that has the problem, but hypothetically speaking, obviously the solution I'm about to give you could apply to anybody because you're just talking about your friend, right? That's a hypothetical situation. Okay? What is the value of hypothetical? It can be applied globally. It can be applied universally. It can be applied to many instances. Okay? And so when we take something like a to the n times a to the m, that looks really calculus-y. Okay? It looks really confusing because there's lots of variables there and you're uncomfortable with it, but it's basically saying you can put a number in for any of these values. Okay? So it gives you kind of a global feel. But we like to work with examples. You come into my office and say, brothers, I have a problem. Okay? Now I can place a name and a face to the problem. I can get very specific in my solutions to the problem because I know it's about you. Right? And so we like examples. They give us a lot more of a concrete understanding of what we're doing, right? So the hypothetical, it allows us to see how it applies to everything, but then we want examples. And this last column here is basically how we're going to identify that all these aren't magical and mystical shortcuts. Sometimes when you look at what they're doing, you're like, what the fetch? How can they do that? It's so magical and mystical, but we're going to bust those myths. So we're going to have our little myth buster moments. Okay, you guys cool? Those are our 4 columns. All right. You guys can laugh. You can talk. We're on video, right? But we do have to work today, all right? But we're not going to go, we can't get into any of these cool conversations we get into sometimes about the meaning of life and all that kind of stuff, or how we're going to be motivated to do all kinds of cool things, because we just got to crank through the math here. And then we're going to make a separate video about the meaning of life. Is that cool? All right, good. We actually are. Okay, kind of. So the first rule is titled the Grace is looking at me weird like, are you wanting me to video the meaning of life? Yes, Grace. And you look very nice today, Grace. You're kind of dressed up today. No? You always look nice. Okay? You dress nicer than I do. That's a fact. All right. Hypothetical. A to the 0 equals 1. Okay? So look up here. A to the 0 equals 1. Yeah. Who said no?
Why is he smoking, bro?
Okay. So let's go to the Mythbuster section over on Mythbuster. Okay? And the big question here is, why doesn't A to the 0 equal 0? Yeah, everybody wants it to equal 0. We'll go back to those 5 things that what?
There's still 1 there. It would be A itself, right? Is the 1.
Let's hang tight. So you're good. I'm going to get there. But here's the deal. Why doesn't A to the 0 equal 0, right? Anytime we see 0, we're like, doesn't it equal 0? Well, we go back to the 5 things that we just talked about. Little numbers and big numbers behave differently. This isn't A times 0. Yeah, that equals 0. But it's A to the 0. Okay? Now, notice that sorry, that's kind of weird drawing of A right now. A to the 1 equals 1. Okay, well, we're like, that makes sense because, 7 times 1, or A times 1 makes A, right? And so you're like, well, I thought you said little numbers and big numbers behave differently. Well, okay, do you behave differently than your parents? Especially when you're children. Do you behave like them sometimes? And as you get older, do you behave more like them? Yeah, so it's not that little numbers and big numbers always behave differently. It doesn't say they always do, but they do behave differently in most instances, but sometimes they behave similarly. Okay? All right, so this was the hypothetical, right? And right now, there's really nothing to write down except the Mythbuster right here, where we're saying, why doesn't A to the 0 equal 0? That's the only thing that I want you to have written down right now. The hypothetical is already written for you, but look at the example. Under the example, it says that 7 to the 0 equals what? 1, and 7 to the 1 equals 7. Okay? Underneath this, yeah.
It says A to the first equals A.
Oh, sorry. Sorry, that should be A. Thank you. Erase that in YouTube land. Go back. A to first equals A. That's right. That's right. Because A to the first should equal 0. Because just like, 7 times 1 equals 7, well, 7 to the 1 equals 7 as well. Okay? They behave similarly in that instance. Thank you. Sorry. So, I want you right now, what does x to the 0 equal? What would x to the 0 equal? It would equal 1. What would x to the 1 equal?
X.
It would equal itself. It would equal x. So go ahead and write that underneath 7 to the 0 and 7 to the 1. Write that additional example there, okay? Of x to the 0 equals 1, and x to the 1 equals x, okay? Now, we're not going to bust this myth just yet. We're going to leave this little quandary in your mind of, why does anything to the 0 equal 1? Why doesn't it equal 0? We're going to leave that there. We're going to bust that myth later, because we've got to develop a couple more skills today, and then we're going to be able to bust that really easily, okay? But right now, it won't be meaningful to you if I put the answer up there. So let's go to our next rule, product rule. So please listen. On each one of these rules. So you want to write something in this box right here. So on the 0 and 1 rule, ready for this? Before you write it, let me finish it, okay? So the 0 and the 1 rules, okay? So we're going to say the 0 rule, okay? It's telling you that any value to the 0 power equals 1. And that's what you're going to write for that. But also, on the 1 rule, you're going to write any value to the 1 power equals itself. Okay? And that's what you'll write inside that little space in there. So you don't have a lot of space in those boxes. So now I'm going to write what you should have underneath, not power. How about the product rule? Okay? Product rule. Let's go ahead and get rid of the pink pen. It might not show as well in camera land. So the product rule, underneath it, and again, before you write this, let me write it, because you got to squeeze it in there, and you might want to kind of look at how you do this. It's going to say that values with same base being multiplied, okay, add the exponents. Okay? So when we have values with the same base and they're being multiplied, we're going to add their exponents. So on the hypothetical, we're going to start writing on the other board too, so the other side of the class doesn't feel neglected. Okay? A to the n times a to the m equals a to the n plus m. Okay? So you already have the a to the n times a to the m there. You're going to write a to the n plus m. Cool? Fill that in. Equals a to the n plus m. On the example, you have x to the second times x to the third. And we're going to say, well, that equals x to the 2 plus 3, which equals x to the 5th. So again, look up here, please. I don't want you to just write it equals x to the 5th. I want you to write that it's x to the 2 plus 3. Okay? So I've already written on it for you. The problem, x to the second times x to the third. So think about that. They have the same base. They're being multiplied. The rule is you add their exponents. So what is the myth buster? What's the myth buster? All right? Well, the question here, and again, I would wait to write this until you see this, but why, the question why isn't x to the second times x to the third equal to what? X to the 6th. X to the 6th, right? Why doesn't it equal that? Okay? Well, we're going to take x to the second, multiply times x to the third. Do you all agree with me that x to the second is x times x? Yeah. Do you agree with me that x to the third is x times x times x? Yes. And we are multiplying those. And so I have a question for you. Okay? What does that equal? X to the 5th. Very good. Does not equal x to the 6th. So we see the shortcut, right? If we expand it all out, it proves that what we're doing is true. So pay attention to this. If I have x to the 25th times x to the 77th, do I need to write 25 x's and 77 x's and count them all up? Nope. I can say that equals x to the 25 plus 77, and that makes x to the 102. Okay? Kind of nice, yeah? That's why we have these laws of exponents. They're nice to have shortcuts. It's like little Brian, who doesn't want to trespass on Mr. LaCroix's yard, and Brother Rich at age 10 is going mafia on him. Brian, let's go. You know? Yeah. That's the way it was. And then we would leave Brian and run through Mr. LaCroix's yard, and Brian would stand there and look at Mr. LaCroix, and Mr. LaCroix would yell at him, and then he'd cry and he'd walk the long way to school. He'd be late and get detention, and then when we got home to, play, hang out, ride bikes, Jeff, his older brother, who's my best buddy, would be grounded because he left his little brother behind, And then he tells Mom, Rich, he's like in the little children mafia. He made me do it, I'm like, I'm not walking the long way, you punks. Let's go. You know, God made this land. Mr. LaCroix didn't. I'm running in his backyard. Okay. Okay. Amen. All right. I'm gonna erase this. You guys okay? I'm gonna erase the left board. The left board. You okay with that? So you're filling in your chart.
Brother Rich, what's
Yes.
the word, the big long word I can't read?
Big long word.
Right under values with the same base.
Being multiplied.
Values with the same base being multiplied. It's two words, being multiplied. You add their exponents. Okay?
Thank you.
So ultimately, the rule is to add the exponents. Okay. You guys okay if I erase this?
Yeah.
Anybody hold off? Tell me now.
Wait, just kidding.
You're a veg.
Come on.
You're giving me undue anxiety. Okay. So our next rule is called the quotient rule. Let's think about that. What did we say on the product rule? What did you write underneath the product rule? What did you write?
Values in the same base being multiplied.
Okay. So this one's going to say values with same base being what? Divided, because quotient means division. What do you think we're going to do?
Subtract exponents?
Subtract exponents. Very good. And that's really good deductive reasoning there, using your God-given gift of common sense, because the opposite of multiplication is,
Division.
and in multiplication we're adding, so the opposite of addition is, so it makes sense when we have the quotient rule, we will subtract, because in the product rule we added. Okay? Hypothetical, a to the n over a to the m equals a to the n minus m. But I want you to write when n is greater than m and circle that. Okay? A to the n over a to the m equals a to the n minus m when n is greater than m. And that all goes right here. A lot of n and m going on, right? And tongue twisting and brain teasing and all that stuff. So what do we write on the bottom? Look at this. It says a to the n over a to the m. We have it again with a line here. Equals 1 over a to the m minus n when m is greater than n. Okay?
What does that tell us? Like, why
So-
do we put when n is greater than n?
Okay? So this is why the hypothetical leaves us with questions. You are guiding us to the example. So the example is going to answer that for you. Okay? So again, remember, the value of hypothetical is it provides me a law that can apply to everything. But then it leaves my brain doing exactly what your brain just did and saying, what the fetch? Okay? So we're going to fetch it up over here. So now, am I good to erase this? Too late? You ain't gonna get me this time. All right? What? But the board is. All right. So we have, for our example for the quotient rule, on the top one we have x to the sixth over x to the third. If you look at the example, look at this, okay? N, top exponent, is greater than m, bottom exponent. Here, 2, n is not as big. M ends up being greater than 2. So you can see the example start to formulate of what n greater than m versus m greater than n is. It's top bigger than bottom or bottom bigger than top as far as the exponents are concerned. First example, look up here. X to the 6th over x to the 3rd will equal x to the 6th minus 3, which equals x to the 3rd. Bottom example, look up here, will be x to the 2nd over x to the 5th equals, we're going to say 1 over x to the 5 minus 2, because we're going to bring this down, because this is bigger here, and we like big minus small, over x to the what? X to the 3rd, also to the 3rd, right? Now let's go ahead and let's myth bust these, okay? So do you agree with me that x to the 6th over x to the 3rd equals x times x times x times x times x times x? It sounds stupid when we say that, doesn't it? X times x times x, right? That's why we take shortcuts. What goes on the bottom? X times x times x equals x to the 3rd, yes? Do you agree that x over x can cancel each other out and make a 1? And that can make a 1, and that can make a 1. So what are we left with on the top? X to the third. Very good. And so we see that, nope, this isn't 6. So we could say to ourselves on the Mythbuster, why? Why isn't this x to the 6th over x to the 3rd equals x to the 2nd, right? Because we could divide them. 6 divided by 3 would make 2. Okay? Nope, we're going to put a, that does not equal it. Equals this when we stretch it out. Let's look at this one. X to the 2nd over x to the 5th. This equals x times x over x times x times x times x times x. These cancel. Big question. Big question. Pay attention. What's left on top?
Nothing.
No such thing as nothing in math. That's not on any number set. So nothing's not an answer. Is it 0 or is it 1? It's 1. Look at it. This is a 1. X over x makes 1 times. This is a 1. X over x makes 1. 1 times 1 leaves you with 1 over what? X to the 3rd. Right? We cool? So indeed, we see that these shortcuts are now busted because we spread them out and it works out. Agreed? Okay. Do you need a second to catch up?
Yes.
Okay, let's pause the video for a second. All right, so the question has come up. Say it again.
How come we subtract 5 and 2 at the bottom
Not on the top.
and not on the top? Yeah.
Okay? So let's go ahead at this point right here, and I want to share this with you. I actually want you, if you write more, so all of what's on the board right here goes in this box of the quotient rule. But now what I'm about to write, you're going to put right here. It's actually the Mythbuster for the negative exponent rule. Please look up here. Do you agree with me that x to the 2nd over x to the 5th, if we did not do this 1 over thing, would you agree with me then, if we just obeyed the quotient rule, that would equal x to the 2 minus 5, right? We take top number minus the bottom number. Agreed?
Yeah.
What does that equal? X to the negative 3rd, right? Okay. So let's pause there for a second, not the video. Let's pause there for a second. Let's come over here, and let's now talk about our next rule. We ready to talk about the next rule? You're like, did you answer my question? I'm going to answer it powerfully for you. Can I erase this board? Okay. So my next rule is called the negative exponent rule. All right? And the negative exponent rule, all right, underneath that, I'm going to tell you 2 things about it. And this, I'm going to tell you, you might want to wait for me to write it all so you can squeeze it all into this box, okay? So the first thing, because I'm going to write it big, first thing you got to understand is that the negative exponent rule, we can't have them, okay? What does that mean? It means we don't like negative exponents, okay? We don't like 2/4 as an answer. We always reduce it to what? 2/4. What do we always call it? 1/2. We don't like unreduced fractions in math, and we don't like negative exponents either. We're gonna change them up. So how do we get rid of them? Okay, so can't have them. Get rid of them. Okay, and how are we gonna get rid of them? You're going to move. Okay, the value with the negative exponent to its opposite place in the fraction, and then the exponent becomes positive. And I told you not to write this until I wrote it all, because there's a lot to write there, and you got to kind of figure out how am I going to squeeze that in there, and you'll be good. So what does that mean? If you can't see it well, you can get up, you can walk over, you can take a picture, you can do whatever you need to do. Check it out. A to the negative n equals 1 over a to the n. Think about this for a second. The value with the negative exponent is going to move to its opposite place in the fraction. Now look up, you may say, well, there wasn't a fraction. Sure there is. There's always a fraction. We just don't see it. because this is over 1, because anything over 1 equals itself. So now we're moving this down, and this magically becomes positive. And we're going to need to myth bust this because that looks like magic. That doesn't make sense. Just magically becomes positive when you bring it down. The next example, 1 over a to the negative m, and it's written over here, but I'm writing it down low so we don't get crouched up here, equals what? We're going to take this to its opposite place of the fraction, up high, and it becomes positive, a to the m, instead of a to the negative m. Okay? That's the hypothetical. So let's do a couple of examples on the other board. Can I erase this board? You guys okay? I'm actually not going to erase all of it. I'm just going to erase the top. Okay? Sure. Okay. Please look up here. I want to keep this because it's going to be part of how we explain all of this. X to the negative 3 equals what? What will it equal? 1 over x to the third. Very good. And then the next example, 1 over x to the negative 2 is going to equal what? X to the second. Very good. Okay? So, I'm going to pause our video for a second, and we're going to give you a second to catch up. Let's do this. Okay, please listen. Because if you're not paying attention, you're going to get lost. Because I'm going to explain the myth buster to this rule here. Please look at this board. You're asking me on this rule right here, why the fetch do we do this twice? Why do we have this as x to the third, but this is 1 over x to the third? Okay, well, because, look up here. If I treat the quotient rule the same always, and just take the top minus the bottom, when the bottom is bigger than the top, I will get a what? A negative exponent. Not a big deal. You can apply the negative exponent rule. What does the negative exponent rule says? What does it say this is?
1 over x to the third.
1 over x to the third. Look here. X to the second over x to the fifth equals x times x over x times x times x times x times x. These x's canceled and left you with what on top? 1. And what on bottom? X to the third. And yet you told me that x to the second over x to the fifth. Look up here. Don't look down. This is important. Same thing. Look up here. X to the second over x to the fifth. X to the second over x to the fifth. Are those the same?
Mm-hmm.
Here you're telling me the answer is 1 over x to the third. And here you're telling me it's x to the negative third, which means these answers are the same. And you just proved the negative exponent rule. It's not magical or mystical. We don't magically get to take it and put it in its opposite place and make it positive. It's because those values are identical. They are the same because of stuff like this. Okay? You good? Let's take another one. Look at this. Just for kicks and giggles. X to the third over x to the seventh. Paying attention? X to the 3 minus 7. Do you agree? What does that equal? X to the what? Negative 4. Let's prove it though. X times x times x over x times x times x times x times x times x times x. That's 7 x's. These all cancel. What's left on top? 1 over what's left on bottom. These 3 cancel out. What's left on bottom? X to the 4th, which means this and this are the same. And that's why we can just use a shortcut instead of writing it all out and just say put it in its opposite place, make it positive, we're done. And so if you don't want to run into that issue when you're using the quotient rule, you could do this or this. So what I want you to write here, and it's actually supposed to be written on here, okay? It's pretty interesting. You're supposed to have an or right here. So write or, big letter, or. And on this one, between these two, you should have and. So write and right there, or and and. I gotta remind myself to do that later. So I'm gonna forget. So I'm gonna write it over here on this board. Or and. Where do we write it? Okay. You're writing or right here, O-R, between these two, because you could do this or this. You could do either way. Here, you write and between these. It's this and this. Those two you have to apply. These you can apply it either way. Okay? All right. Let's talk about the zero rule myth buster. you like to see the zero rule myth busted? So why did we wait? Example. X to the third over x to the third. Do you agree that that equals 1? Anything divided by itself equals 1, yes or no?
Yeah.
Okay? But the quotient rule says that that's x to the 3 minus 3, right? The quotient rule says when you have the same base, you can subtract their exponents. Agreed?
Yeah.
What's 3 minus 3? X to the 0. But you told me it equaled 1. Therefore, x to the 0 always equals 1. Boom. Okay? So we just proved the zero rule. It's not a magical or mystical thing. It's the fact that exponents being subtracted will yield a 0 exponent if they're the same exponent. Right? But anything divided by itself that's the same would be 1. All right. Power rule. You guys want a second again to catch up?
Yes.
Okay, pause it. But not all that we're going to learn today. We have much left to do. We're just learning the rules. Then we got to learn how to apply them. And you're going to find that, you can learn this stuff pretty quickly. The next rule is called the power rule. Okay? And the power rule, underneath that, you want to say everything in the parentheses receives the power. And I think if you spell it that way, it's more powerful. Okay? And not only that, but how's it going to receive it? Through multiplication. All right? And in essence, this is powers being raised to powers, or to greater powers.
So
Okay.
in other words, this is distribution.
Kind of, yeah. I'm not against admitting that. This is kind of like when your wife says, "So you're kind of selfish," and you're like, "Yeah, I can't lie. That's probably true." Okay, look up here. A to the N to the M. Okay, hypothetical, right? We finally get to multiply them. Look up here, please. This equals A to the N times M. Okay? Now, do we all agree? Listen, because I see you guys writing a ton. Power rule is already written. You have to write this, right? This is already written. Agreed? And the equal sign's written. Agreed?
Yeah.
You're just writing this, right? You cool? Don't be writing stuff that's already on here. Don't waste your time. So let's go to the example side. It's going to be on the board. 2 examples. X to the second to the third, powers being raised to greater powers, is going to equal x to the 2 times 3, which equals x to the 6. Yeah. Finally get to multiply them, right? We had to subtract them, we had to add them, right? Now we get to multiply them. Next example, 2x to the second y all over z to the third, all to the third power. Let's drop our pens and pencils for a second and look at this. I think it becomes pretty critical. I think we all could agree that everything in math has an exponent. Sometimes it's just 1, because anything to the 1 is itself, but everything has an exponent. Well, when I tell you in the power rule that everything in the parentheses receives this power, I mean everything. I mean the 2, I mean the x, I mean the y, I mean the z. I mean everything. And so this equals, look up here, this equals 2 to the 1 times 3. 1 times 3. X to the 2 times 3. 2 times 3. This distribution, right, Faye? Okay, y to the 1 times 3, all over z to the 3 times 3, which equals 2 to the third, x to the, help me, 6th, y to the third, all over z to the 9th, because they're being multiplied. Can you call 2 to the third something else? 2 cubed, that's just true. What else could you call it? 8. You can multiply it out. And so, really, there's a rule of thumb in math, and you're not going to like this rule of thumb because it's not a law. It says if you can do it in your head, multiply it out. And people are like, well, my head's different than your head, and his head's different than her head, and we all got different mind space going on here. But the rule of thumb is, simple ones like this: 2 times 2 times 2 is 8, x to the 6th, y to the 3rd, over z to the 9th. You're taking a multiple choice test. All I'm telling you is be ready to change that to this, okay? Either one of these answers is correct, but in many instances, this will be the final answer written. If it was 2 to the 7th, they'd leave it as 2 to the 7th. Because 2 to the 7th isn't something that we can just do in our head quickly. Agreed? 2 times 2 times 2 times 2 times 2 times 2. We're thinking about it too much. All right? Okay. And that is the laws of exponents in all of their glory. Let's pause. Okay? Thank you. So if we are going to myth bust this, all right, it's not really one that confuses us like the others. It doesn't look as magical and mystical. But x to the 2nd to the 3rd, do we all agree that's x squared times x squared times x squared? Yeah? Anything to the 3rd, this x squared to the 3rd is going to be x squared times x squared times x squared, yeah? And then we could say, well, that's x times x, and this is x times x, and this is x times x. These times comes down. And so ultimately, I have 6 x's being multiplied, which makes x to the 6th. Okay, and so we can spread that out and see that, we can, yes?
So if we do have a problem where we have z to the 3rd,
Mm-hmm.
what if we have x to the 3rd and there's 2 exponents that are the same?
Say it louder.
So z is different right now, but what if it was the same as one of the other variables?
Oh, what if this was an x as well?
Mhm.
Well, then we're going to have to simplify those because they're on top of each other. So we're not going to get into that today, but we're going to get into it next week because we're going to start talking about how to simplify expressions and like divide and multiply, what we call polynomials and stuff like that. But I mean, if you think about this though, at the end of the day, let's say that this was x as well. So let's just go ahead, just for fun, even on the camera we can do this. And this is x to the 9th now. Let's say this had been an x down here, okay? It wasn't, it was a z. We saw that it was a z. We wrote it down as a z, but let's say it was x, okay? So here's the deal. The 2 to the 3rd is still 8, and the y to the 3rd is still y to the 3rd, and but down here, that's the bigger one, so this is going to end up being x to the 9 minus 6, because these two have the same base, they can be reduced, which is going to make 8y to the 3rd over x to the 3rd, and we're done. Okay? Okay, it's a cool question you ask. But we're not going to get anything that complex on this assignment, okay? Not yet. All right. So you are to turn your page and be working on, and yeah, we probably want to get out of sideways mode here. You're gonna work on these examples. How about we do some together? Would you guys like to do them together?
Yeah.
Yes, please. Okay. So if we do them together, your job, you listening to me, is to read the problems to me, so I don't have to keep standing and looking, okay? And let's go ahead and let's go ahead and zoom on this just a little bit more. Is that better?
Yeah.
All right. So, can I erase this board here? Everybody cool?
Yes.
Okay. All right.
Wait. I'm just kidding.
Dudes, you gotta stop. It's just way too fun for you. Way too fun. Okay? And the next time you do it, I'm gonna fart out loud. Okay? You give me crap, I'm gonna give you crap. Yeah. All right. 0 and 1 rule. 0 and 1 rule. Read the problems to me quickly.
X to the 0.
X to the 0. Next one.
P to the 1.
P to the 1.
12 to the 1st times 12 to 0.
And
2x to the 0.
all eyes up here. All eyes up here. Let's do these together. Come on. X to the 0 equals what? 1. P to the 1 equals what? P. Got those two right? Say woo. Woo. Good job. You know the 0 and 1 rule. Now look up here. What's 12 to the 1?
12.
It's 12. What's 12 to the 0? And 12 times 1 is? 12. Say woo if you got it right. Woo. Kind of cool. Okay? All right, check this out. This one's interesting. Remember, we learned this a while ago. The exponent only affects what it touches. Is it touching the 2?
No.
So I'm going to write something here that I think would be fun for you to write as well, okay, versus this, okay? 2x to the 0 is 2 times 1 because x to the 0 is 1, and this just makes 2. Say whoa if you got it right.
Whoa.
Okay? But 2x to the 0 would equal what? The whole thing would just be 1 because everything in the parentheses would receive the power. You would have 2 to the 0 and x to the 0, which would end up being 1 times 1, which is 1, right?
Yeah.
Okay. So we don't have that example on there, but I just threw that in as an extra one. You guys cool?
Yeah.
Okay, yes?
Can you go over the 12 times 12?
12 times 12? Okay? Every eye up here. I love this because everybody in the world, listen, wants to say, that's 144, Brother Rich. It's 12 times 12. That isn't a 12 times a 12. That's a 12 to the first times a 12 to the 0. 12 times 12 is 12 to the first times 12 to the first. Okay? Ready for this? Okay? Pay attention to this. Do these have the same base?
No, yeah.
Remember I said that you don't have to clean your bedroom the same way. You can apply the laws, randomly.
Yeah.
Pay attention to this. Same base means you can take their exponents and add them. 12 to the 1 plus 0 makes what? 12 to the 1, which equals 12, right? That's one way you could look at this problem. But what I'm telling you is, take each one. 12 to the 1 is 12. 12 to the 0 is 1. The times comes down, 12 times 1 makes 12. Does that help? Okay, cool. Good questions. Okay, let's go to the next board. You guys help me. Product rule. Okay? Product rule. Read the problems to me. Hurry.
P to the 7 times P to the 12.
Okay, what's my next one?
P to the 3rd times P to the 5th.
There's a lot of P going on here.
Yeah.
Go, keep going.
X to the 2nd times X to the 5th times X to the 12th.
Oh, any more?
X to the 5th times X to the negative 5th.
Ah, yes. Okay, everybody look up here. These are examples of which rule? Product. It's all product. Now remember, what do we do with the product rule? Everybody, what do we do? If they have the same base, we add their exponents. So this is p to the 7 plus 12, which makes p to the what? 19. Say well if you got it right. This is p to the 3 plus 5, which makes p to the what? Say well if you got it right. This is x to the 2 plus 5 plus 12, which makes x to the 19th. And this is x to the 5 plus negative 5, which makes what? 5 plus negative 5 makes x to the, which equals 1. You guys cool? You guys cool? Was that fast? See how when you begin to learn these shortcuts, they start to take root in you, and boom, boom, boom. You can rip and whip these problems out. Okay? Quotient rule. I'm going to erase this over here. You guys cool? Okay. Give me the problems for the quotient rule, quickly. I want the first one. Go.
P7 over P to the 4th.
Okay? Next one.
P16 over P to the 4th.
Over p to the 4th?
Yep.
Okay.
P16 over P16.
Okay.
And then Y5 over Y negative 7.
Y to the 5th over y to the negative 7?
Yeah.
I love it. Okay. These are all examples of what? Quotient rule. Okay. And we subtract, right? We subtract. Always subtract. Okay, seems to draw B today. B. Not like that. Okay. So this ends up being p to the 7 minus 4, which makes what?
P to the 3rd.
P to the 3rd. This makes p to the 16 minus 4, which makes p to the 12. Okay, what did you want to do here? Brain wants you to say 16 divided by 4 is 4.
Yeah.
Okay, and say it's p to the 4th, but you got to subtract them, right? We threw that in there on purpose. What's anything divided by itself?
1.
So you already know that answer is 1, but you could also call it p to the 16 minus 16, which makes p to the
0.
which equals 1. Yeah, there we go again. Okay. Y to the 5th over y to the negative 7. Okay, I like this. I'll tell you why I like it, because you're going to get rid of that negative exponent if you just do this problem correctly, right? You end up with y to the 5 minus negative 7. Minus and minus makes what? Y to the 5 plus 7, which makes y to the 12. 12. Say woo if you got that one right. Okay. Okay. Negative exponent rule. Okay? Negative exponent rule. Read these problems to me. Read these problems to me. I'm ready. Go.
8 to the negative second.
Okay?
6, x to the negative sixth.
Okay?
5x to the negative third. 5x to the second over y to the negative third. 3x, negative 3x to the negative second. And then over y to the negative fifth.
Negative fifth?
Yeah.
Is that all of them?
Yeah.
Okay. You guys cool? All eyes up here. So that's going to be 1 over 8 to the second, which we can simplify to 1 over,
6.
because we can do that one in our head. Agreed?
Agreed.
Great. This is going to be 1 over x to the 6th. Done. This, look up here, pay attention, this is a big deal. The 5 is its own deal, because it's to the power of positive 1. But the x to the negative third comes down, it becomes x to the third. Okay? This one right here, look up here. The 5 and the x squared stay up top. Some people think that this rule is that they swap places. That's not what we wrote. We said the thing that had the negative exponent goes to its opposite place in the fraction and becomes positive. The other stuff is it doesn't have a problem. This is a positive exponent, that's a positive exponent, it stays where it's at. But this comes up top and becomes y to the third, and that's your answer, and you're done. Okay? All right. This one here, look at negative 3 y to the fifth over x to the second. These did swap, but they really didn't swap, but they end up swapping because this has a negative exponent, it's got to come up here and become positive. That has a negative exponent, it's got to go down there and become positive. And then people say, well, what about negative 3? We don't have a problem with negative big numbers. We never have. We have a problem with negative exponents. So the negative 3 stays along for the ride. You guys cool? Okay. Write those down. Let's go to the next page. We gotta hustle. We only got a couple minutes left. Okay? All right. Power rule. Can I erase this?
Maybe.
Give me the problems. Go. Come on.
In parentheses, a to the second over b to the third to the fourth power.
To the fourth?
Yeah.
Thank you.
And then in parentheses, negative 4x to the third, y to the negative second to the second power.
Love it. Go.
In parentheses, 2a to the second power over 3b to the fourth, all over to the third power.
Oh. No, you're good.
That's right.
All to the what?
To the third.
To the third. Is that it?
Yeah.
All eyes up here. Okay? Everything in the parentheses receives the power. A to the 2 times 4 over b to the 3 times 4 equals a to the 8th over b to the 12th. Okay, cool? This one right here, this is going to be negative 4 to the 1 times 2, x to the 3 times 2, y to the negative 2 times 2. It's going to be negative 4 squared, right?
Yeah.
And it's going to be negative 4 squared because everything in the parentheses is receiving the power. It's this negative 4, which means you can multiply that and call it what? It's not a big number.
16.
There you go. It's a 16. Negative 4 times negative 4 makes positive 16. And that's really critical because getting rid of a negative always simplifies things. That will be the correct answer. They will not put this. They'll put this. And it makes x to the 6th and y to the negative 4th. Well, that's going to make x to the 6th, but the y to the negative 4th has to go to the bottom because it was a negative exponent. That's your final answer here. And finally,
Why did that third one?
y to the negative 4th has a negative exponent. Can't have negative exponents,
Got it, yeah.
right? Always got to simplify them so it comes to its opposite place in the fraction. This one right here is 2 to the 1 times 3, a to the 2 times 3, 3 to the 1 times 3, and b to the 4 times 3. So this ends up being 2 to the 3rd, a to the 6th, 3 to the 3rd, b to the 12th. And if we want to, we can multiply those out because that is 8, a to the 6th over 27b to the 12th. Okay? That's your final answer. Okay. Listen up. Y'all listening to me? Grace and I are going to stay here And we're going to do a quick video showing you the mixed answers, okay, on these. And then when you go home, you can practice those mixed ones and check to see if you're doing them correctly. All right? You have a big homework assignment tonight. I am going to change things up. I did have a section 2 for you to do, but we're going to actually discuss that on Monday. We're just going to do section 1 tonight, okay? So the due date will be changing on that one. So, all right?
So is it due tonight or is it due Monday?
Let's go ahead and pause for just a second. All right, so the first thing I want to tell everybody is that if you have felt a little bit intimidated while we've gone through this lesson, then, you know, about half of students feel that way. My best analogy for you is this. Has anybody ever, you know, taken water and sprinkled it on their lawn? Just sit there and kind of hosed it and the water's just kind of spraying on your lawn and it drinks it up, yeah? But as soon as you take your thumb off the hose or the nozzle off of it and you just let it go, what happens to the water? Does it absorb in? Not as well. A lot of it runs off, right? So this is a really interesting concept of kind of like water saturation. The wetting process is interesting. If you sprinkle it and it gets spread out, it slowly absorbs it and it goes deeper and deeper and deeper and it allows a lot more water to go in. All the water hitting it at once, it cannot absorb into the capillaries of the ground and all that kind of stuff, and it runs off the surface, and so you get a lot of surface runoff. Really interesting. Knowledge works the same way. Sometimes when we're studying or we're learning something and somebody's just like, have you ever heard of drinking from a fire hose? Right? That's kind of the analogy that's given, is that sometimes you feel like you're drinking from a fire hose and it's just like shooting off of you and you're getting a little in you, it's choking you, you know. But the bottom line is that we're going to teach you a lot in this lecture today. And if you're feeling a little overwhelmed, then go back and watch it again slowly on the video. Pause, go through things, take time to take your notes. You know, it's this concept of view and review. So when we're sprinkling water, we're hitting the ground with light drops of water. It's going in, and we continually are hitting it, and so we're doing the same thing over and over and over again. And so that's the point is that when you take knowledge and you take it and then you review it again and again, it sinks deeper and deeper and deeper. So for those of you who have seen the laws of exponents before, this isn't going to be the first time. And so your ground is already a little saturated, and so the water is going to go deeper. The knowledge is going to go deeper. For those of you, this is the first time you've seen this, it may be a little overwhelming at first. But the thing I want to reassure you is if you're willing to take the time to view and review this concept of the laws of exponents, it's going to become easy to you. You're going to learn it, but you're going to need to spend some time on it. Okay, this first problem right here, this is what we called, we'll go ahead and do this first. This is called mixed review. Mixed review. Okay, and so this is all 5 of the laws mixed together. And what we'd like you to do at home is we'd like you to practice all of these and then watch the video. So at this point, we've gone through everything on the lecture. I would pause, I would tackle these problems, and then I'd watch the video to see how you're doing on them. We know that y to the 0 is 1, okay, and that's times y to the negative 16th, which just makes y to the negative 16th. The negative exponent rule says we can't have negative exponents. They go to their opposite place in the fraction. This comes to the bottom. This ends up being 1 over y to the 16th, okay? Right here, again, negative exponent rule. Everything in the parentheses receives the power. In this power rule, this is going to be 2 to the 1 times negative 3, b to the negative 2 times negative 3, all over c to the 3 times negative 3. This ends up being 2 to the negative 3rd, b to the positive 6th, because the negative and negative make a positive, and c to the negative 9th. We're going to continue this problem over this way. We know that we can't have negative exponents. This one's positive, so it's going to stay up top. B to the 6th over. The 2 to the 3rd is going to come to the bottom, become a positive exponent. The c to the 9th is going to come up top. This is going to be c to the 9th. 2 to the 3rd can multiply out and become 8th. So this ends up being b to the 6th, c to the 9th, all over 8. And that's your final answer for that problem right there, okay? As we do these laws of exponents, we start getting more and more proficient in them. We just see that, the 5 laws have to be applied, one at a time. Okay, so this problem right here, I don't know if this pen's going to be good enough. No, I don't like this pen. Watch out. Okay, let's go blue. So everything in the parentheses receives the power. The bottom line is the answer to this is going to equal 1 because anything to the 0 is 1. This is going to be, though, 2 to the 0, x to the 7 times 0, because, 1 times 0 and 7 times 0. So 1 times 0 would be 2 to the 0, and 7 times 0 would be, x to the 0, and 2 to the 0 would be 1, and x to the 0 would be 1, and 1 times 1 would equal 1, right? Our next problem here, this is the quotient rule. This one's kind of fun. We can just say this is p to the 7 minus negative 2. Minus and minus makes plus. P to the 7 plus 2. And 7 plus 2 makes p to the 9th. That's your answer for that one. And finally, this one here. Students love, and I remember being a younger student and seeing this and thinking, yeah, 3 times 3 is 9. And I just want to multiply 3 times 3. But that is not a 3 and a 3. It's 3 to the negative 4th and it's 3 to the 9th. They have the same base. When they have the same base, we learn that we can add their exponents. This becomes 3 to the negative 4 plus 9, which makes 3 to the 5th. We would most likely leave that because we can't multiply that out in our head, and so we would just leave that as 3 to the 5th. We have 4 more of our mixed practices on this other board here. Definitely got some product rule here. All these have the same base. We can take them and we can say that this is x to the 2 plus negative 5 plus 10. And so this is x to the 12 minus 5, because I'm taking the 2 and the 10, and I'm saying this is x to the 7. Okay? That's your final answer. Quotient rule, this is y to the negative 5 minus negative 7. This becomes y to the negative 5 plus 7. This becomes y to the 2nd, and we're done. This one as well. This is all the same base, x's. They're being multiplied, so we get to add their exponents. 2 plus 1 plus 0. This makes x to the 3 plus 0, which is just x to the 3rd, and that's your final answer. And again, we have a parentheses. Powers being raised to powers. This is the power rule. And so we have negative, and this is interesting, 1, because that's a negative 1 there, to the 1 times negative 2. We're going to talk about that here in a second. P to the negative 4 times negative 2, and Q to the 3 times negative 2. We know that when we do a power rule, everything in the parentheses receives the power. This ends up being negative 1 all to the negative 2. P to the positive 8, and Q to the negative 6. So now we have to address the negative exponents, because the negative exponents, we say, to be a simplified problem, we cannot have negative exponents. We can have a negative big number, but that's a negative exponent. We got to deal with that. And so this ends up being, think about this, the p to the 8th stays on the top. The negative 1 to the negative 2 becomes negative 1 squared on the bottom, and q to the 6th on the bottom. What's negative 1 squared? Well, it's 1. And 1 times anything is itself, so that's gone, and this is just p to the 8th over q to the 6th. That's your final answer on that one. These are kind of interesting. If we go back over each one of these problems and we look at them, we could say, and I'm just going to kind of identify here, mixed practice. If we wanted to identify, there are 3 laws taking place here. Of the 5, there is the 0 rule. There is the negative exponent rule, and there is the product rule. All 3 of those are represented here. Product of things with the same base, 0 exponent, negative exponent. This one right here, this is going to be the power rule and the negative exponent rule. Okay, you can just look at the problem and identify. Power is raising powers to greater powers. We always have parentheses in the power rule typically. And the negative exponent rule, because we have negative exponents. This is also an example of the power and the zero rule, because we have a zero power and this is a parentheses powers being raised to powers. This rule right here, this would be the quotient rule. Quotient because they have the same, is that a Q?
Yeah.
I did this problem incorrectly. I treated this like it was a P and a P. Those have different bases. Okay, so interestingly enough, this one, I screwed this up. Let's do this again. My bad. Glad we came back to it. If you see me do something like that, you gotta say something.
I didn't see it.
Okay, you didn't see it either, right? I don't feel as bad because Grace is smarter than me, so just stick with that. Okay, if this was P over P, that would be the answer. But that's a Q, and so this problem right here, that's an easy mistake to make. This is going to end up just being P to the 7th, Q to the 2nd. That's the answer. This comes up at the top, becomes a positive rule. So this is not the quotient rule because they don't have the same base. It is actually just the negative exponent rule. Okay? Glad we went back over that. That's awesome. This problem right here, they have the same base. They're being multiplied, so this is product rule. It could be the negative exponent rule too, but because when you add them, the negative exponents take care of themselves, we don't really have to deal with the negative exponent rule. Coming over here, same kind of thing. This is product. Why? Because all the bases are the same being multiplied. We could say again it's dealing with the negative exponent, but it doesn't because it cancels itself out. This one here is the quotient rule. This one did have, unlike the other problem, both of your entities had the same base. And we could say the negative exponent rule applies here. This is interesting. We talked in class about how you don't have to apply the rules in any particular order. There's another way to do this problem, and the way is this. You could say this is y to the 7th over y to the 5th. Okay? Why? Because that has a negative exponent, goes to its opposite place. This has a negative exponent, goes to its opposite place. Then you could apply the quotient rule, which says they have the same base. You could say, indeed, that equals y to the 7 minus 5, okay, which would equal y to the 2nd. Get the exact same answer doing it a different way, and we learned that we can apply the laws of exponents in different order. Okay, again, this is the product rule, the zero rule, and the one rule, all combined, okay? And then this one here was the power and the negative exponent rule, okay? In terms of what examples, what laws of exponents were extracted from these examples. Good luck at home. Got a big assignment. We'll see you next time.